Hi, everybody. Welcome to my talk at the Salt Lake County Watershed Symposium. My name is Meg Wolf, and I am a PhD candidate at the University of Utah. I study hydrology and water resources in the geology and geophysics department. Today, I'm going to be talking to you all about quantifying the effect of ongoing drought in northern Utah streamflow. And I'd like to thank my advisor, Dr. Paul Brooks, for his support on this project, as well as my lab team, Logan Jameson and Bailey Olds. I'd like to also thank Friends of Great Salt Lake for their support in this project, as well as the University of Utah's Global Change and Sustainability Center, Salt Lake City Public Utilities, and the University of Utah. So, as many of you know, we're in the, we just finished up the water year 2021, and 2021 was characterized by extremely low water yield across the state. So you have probably all seen record low reservoir levels presented in the news in the Salt Lake Tribune this summer in July of 2021, where Echo Reservoir was at about 28% in July. Lake Powell was also at less than 30%, and many other reservoirs across Utah were at 30% or below their average filling capacity. You're also all probably aware that Great Salt Lake hit its new record low in July of 2021, where Great Salt Lake's summer 2021 elevation was at 4,191 feet, and its surface area reduced from about 1,700 square miles, where it's average, to about 950 square miles. So Great Salt Lake is important to think about both its depth, but also the surface area that is covered, because it is such a large ecosystem and it supports so much life in Great Salt Lake and its wetland edges. So we think about water year 2021 was really low, but what's interesting is if you think about last winter, snowpack in the Wasatch and the Wasatch Front wasn't all that bad. So this is the figure on the left is from the NRCS interactive map tool. And I plotted April 1st SWE, so snow water equivalent for 2021. And what we see is along the Wasatch Front, we're at 70 to 100% of average with this yellow and green dots. And then if we look at June observed streamflow in 2021, so after the snowpack starts to melt and we start typically getting our big pulse of spring streamflow, June observed streamflow was at 6 to 50% of median. So I asked the question, if snowpacks were close to average this year, why is streamflow so dramatically low? So what I did was I looked at this in the context of streamflow in northern Utah, in the Jordan River headwater catchments and the Weber River headwater catchments. So this figure on the left shows my study region, which includes the 7 major headwater streams that flow into Great Salt Lake and the Jordan River. And then that includes City Creek, Red Butte Creek, Immigration Creek, Parley's Creek, Mill Creek, Big Cottonwood Creek, and Little Cottonwood Creek. And they also included 5 headwater catchments in the Weber River Basin, which include the Weber Headwaters, Chalk Creek, Lost Creek, Ogden South Fork, and East Canyon. And what I did is I looked at the last 118 years, in some cases, of continuous streamflow data kindly provided by Salt Lake City Public Utilities, as well as USGS stream gauges where available. I also downloaded and looked at 118 years of precipitation and temperature using the PRISM tool. And what I can see here is that I plotted temperature over time from 1901 to 2018, discharge over time from 1901 to 2018 in most catchments, and precipitation from 1901 to 2018. And what you can see here is that we have a pretty broad range of temperature regimes here in the Wasatch Front, where warmer and drier catchments are this redder color. So you can think about City Creek being a little bit warmer than Little Cottonwood Creek, which is this blue color. Similarly, discharge is highest in Little Cottonwood and lowest in Weber at Chalk Creek. And again, precipitation is lowest in Chalk Creek in the Weaver catchment and highest in Little Cottonwood Canyon. So what does this mean for stream flow? So what I want to think about is stream flow is surprisingly variable from year to year. This figure on the left shows Big Cottonwood Creek, total annual stream flow on the y-axis in acre feet times 10 to the fourth, which is thousands. So if we can think about 20,000 acre feet, 40,000 acre feet, 60,000 acre feet, there's a pretty wide range of variability in Big Cottonwood stream flow. Minimum was at 20,000 acre feet, maximum at 100,000 acre feet. But what we see is that even if we have near average precipitation, which is plotted here on the x-axis, 0 is average, this results in a factor of 2 variability in our stream flow in Big Cottonwood. So if we have an average precipitation year in Big Cottonwood Canyon, we have seen stream flow in the past that has ranged from about 30,000 acre feet to about 60,000 acre feet. And what that's telling us is that precipitation might not be the only control on stream flow. And so what I wanted to do was to consider other factors that might help better constrain this variability from year to year and help us better understand what's going on when we have an average precipitation year or a slightly below average precipitation year like the water year 2021, and then why we got such record low stream flow values for almost all of northern Utah. So what I did was I considered a couple extra metrics other than just precipitation to predict stream flow over time. And so what I use is winter base flow, which is I use here as a metric to infer groundwater storage over time. So this figure on the left shows a hydrograph for all 118 years of data that I have available for City Creek Canyon. And what we see is that during this low flow phase of the hydrograph, this is considered the base flow phase. In the middle of winter, we don't get rain, we don't get snowmelt, so there's low day-to-day variability. However, that water that's coming out of the stream has to be coming from somewhere. So that water is likely controlled by water that's already been stored in the catchment and is being slowly released throughout the winter. Often, this storage or this groundwater storage is considered to be stationary over time. But what we see is that winter base flow is not only stationary, but it varies significantly over time. We can then use winter base flow as a simple metric to measure the changes in storage over time to help us better understand when storage is below average or when storage is above average. So what I did as a group under my advisor, Dr. Paul Brooks, which was recently published in a paper, Brooks et al. 2021 in Water Resources Research, is we created a stream flow model for the Wasatch Front using multiple linear regression, using this last 118 years of data that we have. And what we did was we first looked at precipitation and its control on stream flow. So annual precipitation versus annual stream flow. And what we see is that annual precipitation does play a major role in predicting stream flow, but it predicts between 44 to 80% of the variability associated with annual stream flow. If we then add in winter base flow, it reduces this uncertainty by almost half. Additionally, if we include spring snowmelt rate and spring snowmelt duration, we further reduce this uncertainty so that we can predict a change in annual stream flow, if we have above average stream flow or below average stream flow, using a combination of precipitation, antecedent catchment storage inferred from winter base flow, and fast or slow spring melt rate. So what does this mean in the context of a bigger picture? So I wanted to think about winter base flow over time and how it controls annual water yield in any given year. So this figure on the left shows mean annual precipitation versus mean winter base flow. And what this is essentially telling us is that, and then this figure shows mean annual temperature and mean winter base flow. And these two figures together show us that our cool and wetter catchments have a higher total annual winter base flow. This makes sense if you think about the total amount of water that's coming out of Little Cottonwood in any given winter compared to the total amount of water that's coming out of Parley's Creek or Red Butte Creek in any given winter. But what's really interesting is that despite this catchment variability under different precipitation and temperature regimes, is that the variability in winter baseflow follows the exact same pattern despite its catchment characteristics. So our warm and dry catchments and our wet and cool catchments follow the same variability in winter baseflow over time. And what we see is that there's this interesting decadal periodicity in winter baseflow over the last century. And what I then asked is that what controls this variability in winter baseflow over time? And why is it important for total annual streamflow? So what we see is that if, as you saw in our multiple linear regression models, that we can narrow that predictability factor by almost half if we include winter baseflow and streamflow predictions. And this is another way of looking at that, is that winter baseflow controls the fractional annual water yield, so the amount of water that makes it to the stream in any given year. It follows a very similar pattern as mean winter baseflow. So mean winter baseflow is here in red, and mean water yield is here in blue. And what's really important about this is that mean winter baseflow is measured before the total snowpack occurs in any given year. So mean winter baseflow is measured before the peak amount of snow accumulates. It's measured in January, and that antecedent conditions before we even get the next winter snowpack, we can understand if we're going to be above average in our streamflow or below average in our streamflow. So I first ask is what controls this multi-year variability in winter baseflow, which will then translate into what controls this multi-year, or what controls water yield over time. So what I did was I created a multiple linear regression model using antecedent climate from up to 10 years in the past. My hypothesis being that if we have water that's coming out of the stream in winter, and it's not controlled by current precipitation like rain, it's not coming from current year's snowmelt in the middle of January, that water and that variability from year to year in our winter baseflow is likely controlled by something that happened in the past. So what I did was I included up to 10 years of previous precipitation, up to 10 years of previous temperature, up to 10 years of previous melt rate. And what I found is that a change in winter baseflow, so my output is winter baseflow, if we're above average in any given N year, or below average in winter baseflow in any given N year, we can use that current year's fall precipitation, the previous year's precipitation from the year before the year we're trying to predict, so N-1, and up to 3 years in the past. Similarly, the previous years of temperature is also important, and up to 3 years of previous melt rate. So what does this mean in context of the 2021 water year, and why streamflow was so bad this year, given an average snowpack? So what we can think about is that the cumulative influence of multiple years on total annual streamflow is influenced by how much water is stored within a catchment and by multiple years of climate in the past. And so if we look back, if we look at water year 2018, we were at about 50 to 69% of average. There's orange dots all here along the Wasatch Front. If we look at 2019, we were slightly above average with 110 to 129% of average. Water year 2020 was about 70 to 80% of average, and same with water year 2021. So the cumulative influence of these 4 years, we can then better understand what our change in winter baseflow will look like. So if, for example, if we're trying to predict winter baseflow for the water year 2021, we can consider the fall precipitation that occurred in 2021, so last October, November, and December, everything leading up to January 2021. We can consider the total annual precipitation from the water year 2020, the total annual precipitation from water year 2019, which was slightly above average, water year 2018, which was significantly below average, the temperature from the water year 2020, which was significantly above average, and then the melt rates that occurred during the water years 2020, 2019, and 2018. And what this indicates is that if we have this cumulative effect of these multiple variables variables from multiple years of climate in the past, we would then, from this regression, all multiplied and added together, we would result in a below average winter baseflow for 2021, which we did see starting out this last winter. We had significantly below average streamflow before we even entered the peak of our water year. So what this suggests is that if we're starting out water year 2021 with below average winter baseflow conditions, we can also expect that our total annual runoff or our water yield for any given year will also be below average. So as we moved into the 2021 water year, we started out with below average conditions that were influenced by climate from the past, our multi-year drought that's been occurring for the last decade. And we can better understand what is then influencing that change in streamflow to be above or below average. So then what we saw was this water year, this 2021 streamflow, was less than 50% of average across almost all of our catchments here in the Wasatch Front. So the take-home points from all of this data and this multiple linear regression models that I've shown you today is first, that winter baseflow can be used as a metric for measuring groundwater storage over time. And we're not trying to understand the total influence of how much water a catchment can hold and then release in any given year, but rather the relative change in a wet or a dry scenario of how much winter baseflow is changing over time from year to year. The next thing is that the change in winter baseflow, or here groundwater storage, controls annual runoff to a higher degree than previously expected. That above or below average winter baseflow is then controlled by multiple years of antecedent climate, and annual runoff is therefore controlled by timescales longer than just one water year. The implications for this project are that multi-year drought or multi-year wet periods, but if we want to think about it in multi-year drought terms, will impact streamflow for more years than previously expected, even if we receive an average precipitation in the next 2 years. And thank you. That's all I have for you today. If you have any questions about this work and this project, you can email me, Meg Wolf, at meg.wolf@utah.edu. You can also find me in the graduate school directory at the University of Utah Geology and Geophysics Department. Thank you so much for your time. And I hope you learned something today from my talk. Have a good afternoon or morning.